Here is a question that troubled physicists for over a century. Every fundamental law of physics works equally well in both directions of time. Newton's equations, Maxwell's equations, even quantum mechanics run them backward, and they are still valid. A film of two billiard balls colliding looks fine played in reverse. So why does a film of an egg dropping off a table, shattering, and reassembling itself look absurd? Why does time only move forward? The answer, when you find it, is not a law at all. It is counting. Entropy, in its plainest form, is a count. Specifically, it counts the number of ways a system can be arranged at the microscopic level while appearing the same at the large scale. An egg has a very small number of microscopic arrangements that look like an intact egg. It has an astronomically larger number of arrangements that look like a shattered egg on the floor. When you drop it, it is not driven by any force toward disorder. It just falls into whichever microscopic state it ends up in, and almost all of those states look like shattered. Disorder wins by sheer numbers. Ludwig Boltzmann wrote this in a single equation, S equals k times the natural log of omega, where omega is the number of microstates. This was so bold, so unfashionable in 1877, that Boltzmann spent the rest of his life defending it. He was ridiculed by colleagues who thought atoms were a convenient fiction, not something real. He died before Einstein's 1905 paper on Brownian motion proved atoms exist beyond reasonable doubt. His equation is carved on his tombstone in Vienna. It is one of the most correct sentences anyone has ever written. So why does time move forward? Because the universe started in a state of extraordinarily low entropy. The Big Bang, for reasons we do not fully understand, produced an almost unimaginably ordered initial condition. Since then, the universe has been spreading out toward the vastly larger number of disordered states available to it. That spreading is what we call time's arrow. The second law of thermodynamics, entropy always increases in a closed system, is not a fundamental law. It is a statistical near certainty. It is overwhelmingly unlikely to run backward. Not impossible. Just so improbable that in the lifetime of the universe you would not see it once. In 1867, James Clerk Maxwell proposed a thought experiment to defeat the second law. Imagine a tiny demon controlling a small door between two chambers of gas. The demon watches individual molecules. Fast ones approaching from the left, he lets through to the right. Slow ones he blocks. Over time, all the fast, hot molecules end up on one side. Entropy decreases. Order from disorder. The demon seems to have beaten the universe. He hasn't. To decide which molecules to let through, the demon has to observe them, store that information, and eventually erase it. Erasing information generates heat. The entropy produced by the demon's memory always equals or exceeds what he saves. Information and thermodynamics are the same thing. The deepest insight here is that the second law, the most reliable law in all of science, the one that tells you cannot build a perpetual motion machine, the one that says the universe will end in cold, spread-out equilibrium, is not inscribed in the equations of motion. It arises from counting. There are more ways to be disorganized than organized, and the universe samples states randomly. We live in the brief window when that sampling still has enough order left to produce stars, chemistry, and people who ask why time only runs one way.